Good morning. A new topic is here for you. Singularities, lesson 1. Let's start. Definitions. The first definition is about a singular points or singularities. Functions which are analytic at all points of a bounded domain except at a finite number of points. These exceptional points are called singular points, or you can say singularities. For example, if suppose I am having the function 1 over z, then find out the point where the function is not defined, z equal to 0. So z equal to 0 is your singularity. So singularity is the point, a singular point is the point where the function is not defined, where the function is tending to infinity, or where the function is not analytic. Such points are known as the singular points. If I say my function is z minus 1, now what are the singular points? Very good. Z equal to 0 and z equal to 1. These are the singularities of the function 1 over z into z minus 1. Now, the second definition is isolated singularity. Now, it's a kind of the singularity named as isolated singularity. Isolated, alone singularity, right? So, a point z0 is said to be an isolated singularity of the function fz if fz is analytic at each point in some neighborhood of z0. For example, I am having the point z0 here. If I suppose to make a neighborhood of z0, now this z0 is said to be isolated singularity if function is analytic at all points of its neighborhood except z0. Suppose this blue color point, here the function is analytic. Actually all the points of the neighborhood function is analytic except z0. At z0 function is not analytic, right? Such point is a singular point. But when it's said to be an isolated singularity, if a point is having the some neighborhood, then function should be analytic at all the points of the neighborhood, right? Of z0. Then we say that z0 is your isolated singularity. Provided one more thing, no other singularity should fall in this neighborhood. This should be a lone singularity, right? No other singularity falls in this neighborhood. Suppose if one more singularity comes inside this neighborhood, then it is non-isolated singularity. All right, it's clear? So I need a function to be analytic at all the points of the neighborhood of z0. Then we say that z0 is your isolated singularity. For example, fz is equal to z plus 3 over z square into z square plus 2. Now in this kind of function, first we check what are the singularities, right? Singularity means where the function is not defined, where the function is infinite, right? And where the function is not analytic. So what are the singular points then? Yes, z equal to 0 and z equal to, yes, put this is equal to 0, you get z equal to plus minus 2 iota. Very good. So I am having 3 singular points, or I am having 3 singularities, right? So these are singularities. Now to check whether these singularities are isolated or not. Isolated means we can find a neighborhood of 0. We can make, suppose this is your 0 point. this is minus 2, this is 2. Now I can make a neighborhood of 0 because 0 is your singularity. If I make the neighborhood of 0, does this singularity reaching this neighborhood? No. Does this singularity is in this neighborhood? No. So 0 is a lone singular point in this neighborhood? Yes. So 0 is your isolated singularity. Now if I make the neighborhood of 2, does these two singularities coming inside this neighborhood? No. If I make the neighborhood of minus 2, does these two singularities exist in this neighborhood? No. So all these singularities are isolated singularities, right? So all these are isolated singularities. So now I am writing z equal to 0, z equal to plus minus 2 are isolated singularities. Clear? All right. Now there is another function. Just listen very carefully about this. This function is 1 over sine pi by z. First, we need to find the singularity. What is the singular point for this function? Where the function is not defined. Yes, sine of pi is 0. At pi it is not defined. 1 pi, 2 pi, then sine of 3 pi is also 0, sine of so on. So sine of n pi is 0. How should I make here n? If I put z equal to yes, plus minus 1 over n, because there is also negative real axis, so I am writing plus minus 1 by n. So at z equal to plus minus 1 by n, we are having the singularity, right? So how many singularities are there? Infinitely many, because z equal to plus minus 1 by n, where n is your natural number. So we are having so many singularities. 1, right? Z equal to 1. Put n equal to 2, then this is 1 by 2, 1 by 3, 1 by 4, so on. And all these singularities are tending to 0, right? 1 by n if suppose, for larger numbers. And also I am having minus 1 by 2, minus 1 by 3, minus 1 by 4, and lastly tending to 0. Not equal to 0, but tending to 0. Very, very, very close to 0. The last one, singularity. Now all these are singularities of this function. Now check whether these singularities are isolated or not. So here is my number line. What is the range for z? It is from minus 1 to 1, right? And all these singularities are between minus 1 and 1. Suppose these blue colored dots are your isolated, first I say these blue colored dots are your singularities, right? Now, if I make the neighborhood of this, I can choose as small as possible the radius so that this singularity is isolated. Yes. No other singularity falling in this neighborhood. Similarly, this is also isolated, this is also isolated, this is also isolated, the positive ones. So plus minus 1 by n are the isolated singularities, right? We can choose as small as radius such that no other singularity can fall in this neighborhood of the point, right? Now what about 0? First check whether 0 is your singularity or not, because we are saying that z equal to 1, minus 1, 1 by 2, minus 2. These are the singularities. These are the singular points. Now check first check whether 0 is singular point or not. Yes, because at z equal to 0 function is not defined. Sign of infinity is not defined. So 0 is also your singularity. But is it isolated or not? So if I make any neighborhood of 0, then so many infinite number of singularities existed in this neighborhood. Why? Because plus minus 1 by n is tending to 0, very close to 0. Your singularity is plus minus 1 by n. So if you choose any very small radius of the neighborhood of 0, then also, because z is plus minus 1 by n, then also singularity is falling in the neighborhood of 0. So many infinite number of singularities are accumulated near the point 0. So obviously, if you draw any neighborhood of 0, there must exist other singularities also in that neighborhood. So we say that 0 is not isolated. So 0 is not isolated singularity, but other blue colored one are isolated singularities. And why this is non-isolated? Because so many infinitely number of singularities are existing in the neighborhood of 0. And what we have said for the isolated singularity, no other singularity should fall in the neighborhood of that point. Right? So what we get, what we conclude, that z equal to plus minus 1 is, these are isolated singularities, but 0 is not isolated singularity. It is singularity but not isolated. Fine? Alright, let's move on to another example. Now function fz equal to log z. It has a singularity at the origin, which is, now you have to tell me, isolated or not. Since every neighborhood, alright. Now first tell me about what is the singularity for this. Where the function is not defined. Yes, what is that point where this function is not defined? Very good. Z at z equal to 0. This function has singularity at z equal to 0. Now check whether 0 is isolated or not. See, if you see on the number line, this is your 0, but there is one remark that log of z is not analytic on the negative real axis. It can never be. It ceases to be analytic on the negative real axis. For the brief description, you can check my stereographic projection notes and argument of log z, the videos you can check. There I have given the brief description for this. So why the function ceases to be analytic at negative real axis. So right now you just have to take it as a remark that log z is not analytic on the negative real axis. So whatever neighborhood you make for 0, there are the points on the negative real axis which belongs to the every neighborhood of 0. But what we have said for the definition for the isolated singularity, 0 is isolated singularity if function should be analytic at all the points of the neighborhood. But here, function is not analytic on the negative real axis. So definition is not done. Hence, 0 is not isolated singularity. It is singularity, but it is not isolated. Right? Because for isolated singularity, we need function to be analytic at all the points, at the negative real axis also. But here function ceases to be analytic at the negative real axis. So whatever neighborhood you can draw for 0, function can never be analytic at all the points of the neighborhood, any neighborhood. So it has a singularity at the origin, which is yes. Now fill up the blank. Yes, very good. Non-isolated, not. Non is also okay. Not isolated, since every neighborhood of 0 contains points on the negative real axis where log z ceases to be analytic. Alright, now a remark is there. Let z equal to z0 be isolated singularity of function fz. Second, since the singularity is isolated, there exists a deleted neighborhood, that is z minus z0 mod less than or greater than 0. So z0 is a point having the radius r in which fz is analytic. Then fz has Lorentz expansion. Fz is equal to infinite sum an z minus z0 the power n plus infinite sum where n starts from 1 to infinity bn z minus z0 the power minus n. Now this is your point z0. I have drawn a neighborhood of z0 having the radius r. So this is your deleted neighborhood of z0 for isolated singularity, right? This second one is your principal part of fz at z equal to z0. We know that this is your principal part and this is your regular part. Now on the basis of the principal part of fz, I am defining some more kinds of singularities in further. Now there are more 3 types of singularities: simple pole, isolated essential singularity, removable singularity. Very easy one. Just see how these are different from each other. First one is your simple pole. Now we have to check the principal part of the function, right? If the principal part of fz at z equal to z0 consists of finite number of terms, say m, so terms should be finite, we say that z0 is a pole of order m of fz. Now if there are m terms, then z0 is having the pole of order m. If there are 3 terms, then z0 is a pole of order 3. If there is 1 term, then z0 is pole of order 1. And if a pole of order 1, then such a pole is called simple pole. Right? Clear? Alright. Now if z0 is a pole of order m, then I'm giving you the example for this. Fz is equal to, let me change the color of the pen. Okay, suppose this is your function. Summation n equal to 0 to infinity an z minus z0 the power n. This is your regular part, but what we are saying, in the principal part we must have the finite number of terms. Now it is written that z0 is a pole of order m, so I must having the m number of terms for the principal part. So this is b1 over z minus z0 plus b2 over z minus z0 the square up to bm over z minus z0 the power m. So this is my function which is having pole of order m. Next, isolated essential singularity. Whatever may be the function, first we find out the singularity and then we check whether it is isolated or isolated essential or removable, right? Now if the principal part of fz at z equal to z0 contains infinite number of terms, then z0 is called isolated essential singularity of fz. For example, e the power 1 by z. This is my function. This function is equal to, it is expressed as 1 plus, sorry, 1 plus, let's check. First of all, before that, please tell me what is the singularity for this function. Just a simple singularity for this function, where the function is not defined at z equal to 0, because at z equal to 0 this power becomes infinite and function is becoming infinite. So what are the points? The points where the function is becoming infinite, or the points where the function is not defined, or the points where the function is not analytic are the singularities or singular points. Now at z equal to 0, the function is not defined, or at z equal to 0 function is infinity, right? So z equal to 0 is my singularity for this function. Now to check whether this singularity is essential, isolated essential singularity or not, for that I need to check the principal part, the number of terms for the principal part. Now let's express this e the power 1 by z. Yes, this is equal to 1 plus 1 over z plus 1 over z square plus 2 factorial. Wait. This is 1 over z square into 2 factorial plus 1 over z cube 3 factorial, so on. Now this is up to infinity. Okay, how many number of terms I am having in the principal part? Yes, 1, 2, 3 up to infinite. So I'm having infinite number of terms in the principal part. So z equal to 0 is, yes, isolated essential singularity. Clear? Alright, next, removable singularity. Now third is, if the principal part of fz at z equal to 0 consists of no terms, then z0 is said to be removable singularity of fz. So I do not have any principal part term, right? There should be no term of the principal part, then we say that this singularity is removable. For that, I am defining a function as sine of z over z. Yes. First tell me what is the singularity for this function. Where the function is not defined, obviously z equal to 0 is the singularity. Now it has at z equal to 0, I'm checking the singularity is removable or not. Let's express this function 1 over z. Can I express sine z as z minus z cube over 3 factorial plus z the power 5 over 5 factorial? Yes, obviously. This is equal to, yes, multiply 1 by z with each term, this will be 1 minus z square over 3 factorial plus z4 over 5 factorial, so on. Is there any principal part? Is there any principal part in this? No, because for the principal part, z comes in the denominator, right? So, so this function has no principal part, no term of the principal. This function is having no terms for the principal part. Hence, z equal to 0 is removable singularity, right? So thus sin z over z contains no negative powers of z. Whenever you are having the negative powers of z, that means you are having your principal part lying in that function. So this function contains no negative powers of z. So it has removable singularity at z equal to 0. I hope all the differences are clear to you. Just revise whole this video again. We will be doing some more theorems and questions in the next part. Thank you for watching this video. Have a very nice and blessed day. Goodbye.